So welcome to this. Am I audible? Yeah. Welcome to this afternoon. Second session of today, where Professor Munavalli, Guru R Munavalli, he's from Walchand College of Engineering, Sangli, and you please note that he did his PhD under Professor Mohan Kumar, if I am right.
Yes, sir.
And he just did lot of work on the quality aspects, particularly in an urban water networks. And he did it on, he used Epanet at that time, you just imagine. And he worked on quality of distributed water in urban water networks. And also he did modeling. And did his PhD from well-known Indian Institute of Science, Bengaluru. Note that most of our speakers, they are either one way or another way, they are related with ISC Bangalore. Most of our speakers. You take Dr. Danya, you take Dr. Meenu, or you take Professor Mohan Kumar, you take Professor Muzumdar. Okay? Most of our speakers, including Dr. Munavalli, even in they are either related with ISC Bangalore in one way or other way. So it's a prestigious institution. So from that institution only, Professor Guru R Munavalli has got his PhD at that time, and we also worked together some years back. Okay? We are in the same institution. And when I was with Tata Consulting Engineers at Mumbai, also I was interacting with him a lot, and even at IISc also. Yeah. So with such a brief introduction, okay, I am just requesting Professor Munavalli to start his work on this quality of distributed water in urban water networks. And note that after deliveries of his expertise, he will interact with you people a lot, okay, at the moment. Okay. So, sir, Professor Munavalli, sir, please.
Okay. Thank you, Professor Shiva Prasad, for your nice and kind words of introduction of mine. So, before I begin my talk, I would like to thank Mr. and Mrs. Shiva Prasad, Jyothi Prasad, for considering me for this particular FDP as a resource person. So I'll be happy to interact with the variety of people in this particular group, including the professors, associate professors, assistant professors, and research scholars. And I also thank the authorities of the Pant University for accepting the recommendation of Professor Shiva Prasad for my candidature as a resource person. So actually, Professor Mohan Kumar has made my job a little bit difficult, because actually he talked about so many things, and whatever I'm going to talk today, he has also covered a part of it. And whenever I talk on the quality aspects of distributed water, so with due respect, I owe my work to Professor Mohan Kumar, because under his able guidance, so I could complete my PhD work in the topic that I'm going to address it today. So actually, the theme of this particular FTP is urban hydrology. Many people have talked on the primary urban hydrology. Primary hydrology, that is my terminology. It is directly concerned with the natural water, its flow, and water balance, etc. But the thing that I'm going to talk today, it is something is associated with the urban hydrology that I can refer in my own way as a secondary hydrology, because the water that is in a nature, that is supplied to the public, and after usage by the public, again it goes to the nature. So it is somehow connected to the urban hydrology. In that sense, I thought that I could share my little bit knowledge or the work experience that I had working with this particular area. So in that sense, I consider it as a little bit a a secondary contribution to the theme of this particular workshop. And I have prepared my line of presentation in this particular way. So normally I have got a habit of starting from the sketch. So I don't know whether it's a good habit or a bad habit. Normally I start building up the theme with the basics. And whatever Professor Mohan Kumar has talked in his lecture work, I attended his full lecture today. He talked of chlorine attenuation, sensor-based monitoring, so many things he has talked. And I will be preparing a fundamental background for those who could not get into those terminology that were explained by Professor Mohan Kumar. Actually, a backward or a inverse kind of a thing. Studying advances, then coming back to the. So I think there are some. Professor Shiva Prasad, there is there is some disturbance in the disturbance from the audience. Please ask them to mute their mic. So I hope the slides are clearly visible and my voice is also clear. Can you confirm, Professor Shiva Prasad?
Yes, sir. Yes, sir.
Okay, so that I can go comfortably with confidence.
Sure. Yes. Okay. I muted all.
Okay. So this is the line of my presentation. So I'll talk something in general about the water quality. Then I'll come to the current practice of water supply system in most of the cities in India. Then I'll focus some initiatives or the fundamentals of water distribution system. Then I'll talk a little bit about the quality of distributed water, and then I'll focus more on the quality concept that is adopted by most of the municipal authorities. That is the presence of chlorine in the water network. Then I shall touch upon some of the modeling concepts which are hydraulic and water quality based. So then we'll see what kind of computer based models or the software that are available in this particular area. Then I'll demonstrate some of the case studies so that I have worked with, and then we'll see some complicated problems that one can visualize and solve in the form of calibration and source strength. Then I'll talk in general about the computer models and their application. Now let us look at the water quality in general. So normally we cannot think of our life without a clean water. And because of that, people are depending on the packaged drinking water. Whenever you go to a hotel, if that hotel person asks you whether you require a municipal water or a packaged water, normally we say that you give a bottled water. That is where the quality concept gets initiated. And that's why we say that clean water is a life. And our quality of life, standard of life is basically governed by this water quality. Normally it is said that healthy people in a healthy ecosystem. So that is basically governed by the water quality that is supplied by the public water supplies. And as you know that most of the diseases are waterborne. So if you don't have access to a potable water, then we are going to suffer with a lot of waterborne diseases. And continuous usage of a relatively bad quality of water, especially in the rural area. So that may have a long negative impact on the health of most of the rural area, because the quality concept is more appropriate or more widespread in the urban area, but the quality concept is not that widespread in the rural area, because the general saying in the rural area, because I have stayed in the rural area for more than 15 years of my life, the concept is even if we drink a turbid water, nothing is going to happen to us. We will be get immunized. We get a better resistance to protect against ourselves. This is kind of a logic that is inbuilt in most of the rural people. But nowadays that concept is not at all applicable, and we need to stress upon a good quality of water for even the rural population as well. And the things are more complicated because most of the natural water available in nature, it is polluted, and that has made the job difficult for the water supply authorities. So in general, a clean water is going to affect the economical health and the social life of any particular locality. So in that sense, clean water, potable water is a must for any development of a community or a area or a city. And if you look at this particular picture, so this is summarized as a centralized water supply system. Nowadays, there are concepts like centralized techniques, decentralized techniques, centralized treatment system, decentralized treatment system. That is more applicable for the water and wastewater areas. So this is a typical centralized treatment system. So that is normally referred as treat and supply. So what we normally do here, we collect the water from a source, maybe a river, maybe a groundwater, maybe a reservoir, maybe a lake, any large source that is selected, and from that source the water is lifted by the conveyance system, pump and rising main, and it is treated in the water treatment plant, and then the pure water is pumped and stored in a number of elevated reservoirs, and then it is supplied to the public through the water distribution system. And if you can see the three different colored dots that are put over here, black, yellow, red and green. These are symbolic representation of a quality of water. We may receive black water, we may receive very good quality of water, we may get a corrosion laden water, we may get a highly chlorinated water. You cannot foresee or you cannot predict what kind of water that is going to come at your tap on any day. So in that sense, the water collected from a common point, treated at a common point and supplied to the consumers. So this entire system is normally referred as a treat and supply system. And you can take any water supply system, right, from a village to a metropolitan city. Most of the water treatment systems or the water supply systems, they follow this particular concept, treat and supply concept. And in this treat and supply concept, the treatment is very important. So like I said earlier, most of the people follow this kind of a concept, and most of the treatment plants in India, they follow a typical set of treatment that is normally referred as a conventional water treatment, wherein the river is a source of supply, and then we use the cascade aerator for getting rid of the dissolved gases. Then that is taken to a coagulation and flocculation system, wherein the solids are built up, suspended solids, and then that is taken to a settling tank where the solids are settled down. And to further bring in the clarity to the water is filtered, and by the time the water reaches the end of filtration, it is a clear water, but still it has got some bacteria in that are called as the pathogens, and that is treated by the chlorination, and the chlorinated water is supplied to the public. So typically, this kind of a water treatment is followed in most of the cities, except some modifications like the use of dual media filter or maybe use of a tube settler, etc. So ultimate objective is to make a turbid water and pathogen-led water free from turbidity and free from the pathogenic content. So like that, the water is treated in the treat and supply system. And so if you look at this entire system, there are some issues that we need to look at. And these I have put in the two categories. One is a challenge, other is a handicap. Whenever you are dealing with a large quantity of water and its treatment, it is very difficult to manage. It is very difficult to operate, and it is difficult to satisfy the requirement of the people. The satisfaction may be in terms of quantity. The satisfaction can be in the form of a quality. So in that sense, I have put, there are so many other challenges, but I identified only these three challenges which are going to be very important. One is the municipal authorities struggle to meet the drinking water quality standards. IS 10500-2012 is a drinking water standard, so that we need to refer to. And to satisfy the standard, not at the end of the treatment is important. Satisfy the standard at the consumer point is very important. So in that sense, the challenge is to put the water treatment plant in a better condition and see that the distributed water reaches the last or the remotest consumer with the same quality. Then they need to have a challenge of maintaining the system, because if you see the treatment units that I have shown, most of the units are mechanical units, and as you know that any mechanized system requires a proper operation, proper skill in the operation, and proper maintenance. So that is a challenge that the municipal water work authorities have to face. And most importantly, when the water is treated in the water treatment plant, we don't only get a clear water, we get a waste also. The waste can be in the form of a filter backwash, the waste can be in the form of a settled sludge. So the disposal of that can itself be a challenge. And to meet these challenges, the municipal bodies or the municipal authorities have got some handicaps. These are general handicaps. The fund available may be less. They may not be able to generate the revenue. The people may not be pay the water bills, etc. So because of the lack of funds available, anything that is to be repaired, replaced, that will be a difficult task. And use of the mechanized units require skilled people. And when the laborers are not skilled, they are not properly trained, then these challenges cannot be properly addressed to. And more importantly, if you want to purchase anything, they have to follow a cumbersome purchase formality. So because of these handicaps, the challenges in some cases, not in all the cases, may not be met. But this is a fact that is true, that is experienced by most of the water authorities. But in spite of this, in spite of these handicaps, I have just collected a recent photograph, because recently the Sangli has suffered with the flood problem from the Krishna river, and the water treatment plant working during the flood time has got this kind of a water. So you can see this is a river water that has entered into the water treatment plant at Miraz. Actually, Miraz and Sangli, they are the twin cities. And after the settling, the treatment plant could give such a quality with a turbidity of less than 1 NTU. And after filtration, still it has got a better quality. I have showed this particular slide because everywhere we don't have a poor performance. At some treatment plants, because of the efforts taken by the concerned engineers, concerned operators, the systems are kept in proper condition, and they could get a quality from a 346 NTU to a less than 1 NTU. And there is a commendable job that is done by the people. But you can see the other pictures also. Other in the sense, the water entering at this and arriving at this in the tap of a consumer. That can be also a possibility. That is the worst possible situation. But in spite of all these efforts, still we see such kind of pictures, such kind of treatment units in most of the institutions, most of the offices, in our own households, and the people, you can see the people carrying the 20-liter can, 10-liter can of packaged drinking water with them. And most of the hotels, most of the restaurants, they serve the packaged drinking water. In spite of having such a public water supply system properly maintained, still we see such a kind of a picture. Point of use purifiers, the use of the wide use of packaged drinking water. Why? And the answer to this question, why, is this is not the answer. I got another question to you. Why? Also, we read the reports from the newspaper. People started getting a red water. People started getting a gray water. People started getting yellow water. And worst case, people have started getting a black water from the distributed water. And I have taken only 2 samples of the newspaper report from internet, but you must have also read that, you must have also seen that. And this is the report indicating the contaminated water reaching the customer, reaching the consumer tap. So like that, these 2 things, one is the use of point of use purification, and the other, the news about a bad quality of distributed water, is because of these 2 reasons. One possible reason is the source of supply itself is a culprit, or even if you have got a very good source of supply, properly working water treatment plant, still you find such a kind of a situation. And in that case, the culprit is the water distribution system. So if the source itself is bad, then nothing is in our hand. We have to treat it. But if the water distribution system itself is going to be a agent for deterioration, is a cause of deterioration, then it needs to be thought of in a proper manner. So in that sense, the two possible reasons for the use of packaged drinking water or the use of point of use purification or to read the news articles on contaminated water is either a source of supply or the water distribution system. Now let us have a look at the actual condition of a source that we use as a water source for a treat and supply kind of a system. So I think this is a river, that is Mandavi River in Goa. So I have taken this photograph from one of the internet resources, and this is the report that is published in a Deccan Herald by Jal Shakti Ministry, indicating that 17 rivers in Karnataka are highly polluted, and it does not require a proof. Whenever you just have a visit to any river bank, you can see the quality of the river, how bad the river is. So for that, we don't have to get any copyright picture, we don't have to refer any internet. But for the sake of simply giving some picturesque background, in this presentation, I just selected two of the sources. I will be showing you one actual source that is near Sangli in my next slide. So you can see this is the Krishna River, and the Sangli, where I belong to, is on the bank of Krishna River. So this is the Google map of Krishna River. So this is a Krishna River stretch meandering, and this is the place called as the Sangli. And if you can see the schematic diagram, it is contributed by so many nalas. And these nalas are not the natural nalas, but the wastewater has acquired that, or the wastewater is flowing in that particular nala. And one of such a stream that I have shown over here. So this is the stream that is more popularly called as the Sheri Nala, which carries the most of the municipal sewage from the Sangli city, and that enters here. And if you can see one more worst possible situation, this is another sewage drain that directly contributes its wastewater to the Krishna River. You can see here. So this is a drain that comes from along the bank of a river, and there is a barrage here. On the downstream side of a barrage, the wastewater is being contributed. And if you are drawing the water from such a contaminated river and putting it to a water treatment plant is supposed to remove the suspended solids and the bacteria. The water treatment plant is not supposed to remove the BOD and COD. And if you are treating that water and supplying to the public, then you can imagine how this source can affect the quality of the water reaching at your tap. So this is actual situation in the Sangli. And to quantify the characteristics of the river near Sangli, one of my MTech students carried out a year-long study, and it was found that it is contaminated with the organic matter, and the DO levels were very low during the summer season, and in the winter, in the rainy season, the quality of the river in terms of DO was relatively better. But most importantly, you can look at this particular figure. So this is the waste load that has been contributed into Krishna River by the disposal of wastewater from the Sangli city. So these two slides, the actual wastewater entering into a Krishna River and its quantification in terms of dissolved oxygen and biochemical oxygen demand, that is a representative of a pollution, indicates how polluted is a river. So I just given one example, and you can also have assessed the reports of many rivers polluted in India, and Krishna River is one of the polluted rivers in India. So like that, when you are getting such a source with a bad quality and putting it into a treatment, and then you are supplying the water, because our water treatment plants are not designed for the removal of BOD or COD. The water treatment plants are designed for removal of suspended solids and the pathogens. So in that sense, the source itself can be one of the possible reasons why we are reluctant to use the municipal water, and we have accepted the packaged drinking water or the point of use purification as a means of getting a good drinking water quality. And the second possible source of contamination can be water distribution system itself. So as we know that the water distribution system especially starts after the water treatment plant. So the pure water rising main, then the elevated reservoirs or the ground level reservoirs, and the different diameter pipelines of different material. These are the major components of any water distribution system. And depending on how they are arranged, so they are given by some fancy names like branch looped, partial looped, etc. But in practice, it is a mix of all these kinds of pattern. But most importantly, when we look at the water distribution system, it has to serve us in some typical requirements. One of the major thing that I expect out of a water distribution system is I should see no contamination, or the water quality should not get deteriorated. The quality at the end of treatment plant should be the quality at your consumer tap. So in that sense, the water distribution system should not play any nuisance. It should not deteriorate the water quality. That is one of the basic requirements from the water distribution system. And I should see that there should not be any cross connection with the sewer line. So we will be talking of that little later in detail. And it should not pose any difficulty in the operation and maintenance, and it should provide us a good quantity of water in a relatively less time. That is, it should have adequate residual pressure available, and most importantly, it should be free from leakages. So in the morning session, Professor Mohan Kumar was talking about the leakages, detection, and other things, because we are losing about 15 to 20% of the water through water distribution system. Which water we are losing? We are losing a treated water. We have spent some money on that. When you are losing a treated water from a distribution system, you are actually losing the money. So if you can save this 15 to 20% of the water, that can be used for some potable or useful purposes. So in that sense, the expectation from the water distribution system is it should be leakage free. And everybody knows that most of our cities in India, they are supplied with intermittent water supply. If I take a case of my own city, Sangli, we have been served with water for 1 hour in the morning and half an hour in the evening. And you can see that requirement of 24 hours being supplied in 1 hour and half an hour. How efficient is the water supply system, or how efficient is the distribution system? And hardly I could collect 300 to 500 liter of water in my storage tank. That itself indicates at what pressure I am getting the water. And for collecting 300 liter of water, I have to wait for 1 hour. And my requirement is about 1,000 liter a day. So that is how the intermittent supplies work in our areas. And nowadays, with the concept of smart cities, 24/7, such kind of fancy words, the people have started to think of continuous water supply. And there are some cities, this may be a practice, or some of the cities may be served with 24/7 with some automation and other things. But in general, I can have two kinds: intermittent supply, that is more widely used, and other is a less widely used concept, the continuous water supply system. And most of the supplies are by this kind of a working. Treatment plants, we use a pump the water, store in the elevated reservoirs, then we supply it to the public. So that is basically called as a gravity cum pumping kind of a system. Pressure and gravity fed systems are normally not applicable for a topography which is a flat in nature, but in a undulated and hilly region, one can think of a gravity fed kind of a system. So whatever some basics I told about layout and other thing, so this is what is in the picture. Whenever you look at the any water distribution system, it is basically governed by the kind of road pattern we have got, or the kind of a road layout we have got. So typically you can see typical zone in any city or in any town, a system looking like this: water treatment plant, elevated reservoirs, and differently arranged, randomly arranged, dead-end pipes, loop pipes, so many combinations you can find in this particular combination. So ultimately, this is the one that we need to deal with. Normally, when I look at the water distribution system, as I told you earlier, there are two aspects. One is the hydraulic aspect, and the quality aspect. So to summarize the hydraulic aspects, whenever I look at the hydraulics of a water distribution system, I need to look at the pipe roughness. And this is one of the key parameters in any hydraulics of water distribution system. Because when the pipe is laid new, it is a smooth, very less resistance, it has got more Hazen-Williams coefficient, and then less Darcy effect for friction factor. But as it grows in the age, the friction will increase, roughness will increase, then that is going to affect the loss of head. So that is for the existing water distribution systems, finding the roughness itself is very key, very important. Then we'll be worried about the flow and velocity of flow and velocity in the pipelines. That is another hydraulic aspect. And how much head loss is occurring in the different sections of the pipeline, and what are the nodal demands which are either governed by the supply or which are governed by the pressure in place, and most importantly, what is the residual pressure available at the nodes of the junctions, and water level in the reservoir. So all these parameters which normally convey something about the hydraulic part of a water distribution system. Now let us look at the quality aspect, quality of a distributed water. The quality, I am looking at the quality here, because even if the source is of not that good quality, water treatment plant is there to make it a good quality. So I am talking of a quality available at the end of water treatment and the quality that is available at the consumer end. So whatever node and see that I have represented over here, this is the quality that I am expecting, and this is the quality that is available. To make it more symbolic in nature, I have just shown a chlorinated and filtered water available at the water treatment plant. And you may have a similar water, available at the consumer, or you may have a water like this at the consumer end, indicating a turbid water. So it means that even a good water quality given by the water treatment plant may not retain its quality. Somehow it gets deteriorated, it will become turbid. And what has happened, source is not a problem, treatment plant is not a problem, but the distribution system is going to be a problem. So in that sense, the water quality is likely to change between this point and this point. And if you have got multiple sources, like another source of different quality, even if these two sources of different quality, and even if the distribution system is not going to contribute any on its own, then the mixing of these itself can be resulting into a different water quality available at the nodes. So this particular sketch symbolically represents the quality of distributed water in which the changes are likely to occur, may occur or may not occur. Now let us try to find out the reasons behind this, why the water quality is going to change in the network. There are some parameters that I just listed out. The first one is the WTP itself. As I told you earlier, when your source water itself is chemically and biologically contaminated, and the water treatment plant is not sufficient to treat it appropriately, and ill-treated water in the sense the treated water not satisfying to the drinking water standards, put into the water supply system, put into the water distribution system, so that may further gets contaminated, and so that will affect the quality at the consumer end. So in that sense, if the treatment system is not effective, the treatment system is not efficient, then you are likely to get a bad water quality, non-potable water quality at your end. That is one thing. The second is if the treatment is inefficient for bacteria removal, pathogens are not removed, or the chlorinator is not working, or the chlorine dose is not appropriate. So in that sense, what may happen, some of the bacteria will escape and they will go into the water distribution system. And whenever a bacteria gets a surface to develop, and whenever a bacteria gets a proper environment to grow, it will grow like anything. And one of the best place for the growth of the bacteria is a pipe, because the pipe is going to bring a dissolved oxygen in that. It is going to bring some nutrients in that, and the inner surface of the pipeline is going to provide a proper shelter or the proper surface for the growth of the bacteria. So in that sense, escaping bacteria may find a very good house in the form of a pipeline, and they will build up their own home and they will grow on inner side of the pipeline, and that may get into a contamination of the water. So this is because of what? This is because of your inefficient treatment, and ultimately the quality of the treated water is important. If you are sending in a properly treated water satisfying drinking water quality standards, then no problem. In that case, this is not a factor. Otherwise, this is going to be a major factor in the water quality variation. The second one is just I told you, when a system is supplied with multiple sources, and if the sources are having different qualities. For example, if you are supplying the water from a ground water as a source with a less hardness in that, and other sources surface water, still lower hardness, and when you mix these two waters and supply it, and you are going to get a different proportion of mixing, and the blending will result in different quality altogether. That is another possibility. So this fact is not applicable if the single source is the supply source for the water network. But this is the major one: age, type, and maintenance. Because most of the water treatment systems, so they are age old, especially when the age of the treatment system is more than 20 or 30 years. Earlier, people used to have a cast iron pipes in the distribution line, and they were unlined CI pipes. Whenever you don't have proper lining for protecting against the corrosion, then the inner surface will get corroded, and that corrosion end product can be a reason for the deterioration in the water quality. So like that, age-old pipes are normally subjected for some kind of a coating, some kind of corrosion, and the maintenance also plays a very important role. So if a system is not properly maintained, then that improper maintenance can also be a part of this thing. I'll just highlight that a little later. Considering the type dead ends, if the water is being continuously circulated without any stagnation, then normally a circulating water is of good quality. But whenever the water becomes stagnant and dead, then it will start behaving like a settling tank, mini settling tank. Solids will settle down, and then you will have a problem with the water quality. The leakages are very risky and dangerous, especially in the intermittent supply. I'll just highlight a case. Suppose there is a leakage occurring in an intermittent water supply system. As we know that in the water resource system, we have a pressure flow, or it is a pressurized system. In the pressurized system, if you have got a leakage, the water will come out. Water will come out. If it is combined with the intermittent water supply system, whenever the supply stops, then the conditions within the water distribution system, they are depressurized. The pressure will reduce in the distribution system, and whenever the pressure reduces, the ponded water in the leakage spot will get sucked inside. All your water pipelines will be filled with the dirty water, because the ponded water, turbid water with a lot of contamination goes into the pipeline. And when the supply starts again, being an intermittent supply, whatever water that has been sucked in earlier, so that will move through the pipeline and it will spread all over the distribution network, and a parcel of this water may reach your water tap, and you start getting a bad quality of water. So in that sense, if it's a continuous supply, leakage may not be that problematic, but in intermittent supply, leakages are very risky and dangerous. And if the pipes are of metallic in region, inner surface not properly protected against corrosion, then the corrosion end products can be a cause of water quality variation. And cross connection with a sewage. I will show a photograph little later, so that will explain everything about this. And this is another factor, so that is very useful for bacterial growth, alternating filling and emptying, especially the distribution pipelines at a higher altitude. They are subjected for filling and emptying, especially in the integrated water supply system. During the supply, they get filled, and during the non-supply, they get emptied. So it is something like a proper ventilation within the distribution pipe. Ventilation in the sense, when it is empty, you have got plenty of oxygen. When it is full, it is going to bring the food for the bacteria. The bacteria which are already present in the distribution pipeline, they get better condition. They get oxygen and they are empty, and they get a food when it is flowing. So in that sense, the bacterial growth is enhanced, or it is pushed under such conditions. So in that sense, the water distribution system with different these parameters is going to affect the water quality variation in the distribution system. And there are some mechanisms or the reactions that are going to occur within a distribution pipeline, and these can be referred as chemical and biological transformation. I can add one more to this, physical transformation as well, because when the water becomes stagnant, either because of the low velocity or because of the non-supply in the low elevated pipelines, the pipe itself will start acting as a settling tank. The solids will settle down, provided the solids are already there in the water supply. Normally, I have got a habit of looking at my overhead tank that is filled with the municipal water. So after 1 month or 2 months, normally I say that see that there is a layer of a clay or the soil particles deposited on the bottom of the tank, and I don't use any other source. I use the municipal source, but still I find the suspended solids. I am getting the treated water suspended solids from where they have come. There is no other source. That itself indicates that your water supplied will have the suspended solids. Like I have experienced the suspended solids being settled in my overhead tank. Every pipe section will act as a settling tank, and the solids are bound to settle down. So in that sense, the physical transformation can occur in the distribution pipeline. And one of the good example of chemical transformation is, if you have got a chlorine as a disinfectant, the chlorine will react with the organic and inorganic compounds and get reacted and get consumed. We will be talking about this little later in detail. This is one of the chemical transformation that can be a possibility. And the most important in the Indian context is, our water resources are polluted. Dissolved organic matter is present, and we don't remove dissolved organic matter from the water treatment plant, and we are chlorinating the water. And when this combination of chlorine and the chlorine residuals, they react, they are going to develop a byproduct that is normally called the disinfection byproduct, and that is known by a name trihalomethanes. These are actually chloro-organic compounds that are likely to get formed because of the interaction between the chlorine, especially free chlorine, and the dissolved organic matter. And this is carcinogenic in nature. That is why we should not be happy that we are supplied with the chlorinated water. If you are supplied with the highly chlorinated water, then this is another danger that is waiting for you. So in that sense, this is another chemical transformation that is likely to occur in the chlorinated water and with the presence of dissolved organic matter. And another biological transformation is the growth of biofilm. Just now I was referring about the bacteria getting a shelter in a pipeline attached to the inner surface of the pipeline, and it is being grown in a layer, and that layer is normally referred as a biofilm. And this bacteria will keep on growing, keep on dying, keep on entering the water supply, and keep on contaminating the water supply or the supplied water to your tap. So this is because of a phenomena, growth of bacteria, biofilm, thickness will increase, it will get sloughed off, it gets detached, and that is going to contaminate the water. And all these reasons, there is the blending of a water, contribution by the water distribution system, or the bad source, ineffective water treatment plant, ultimately is going to affect the temporal and spatial variation of the water quality. The meaning of this is every day in my house, if I am getting a water quality, at the same time, I may not get the same quality next day, or whatever the water quality that is in my neighbor, I may not have the same quality. Like that, location wise it may change, time wise it may change. That is the ultimate effect of these variations. And this is a schematic representation of the summary of whatever I discussed till now. I told you that I am going to show a photograph in which I will highlight the cross connections. So you can see this is a case of a cross connection. So this is actually a drain, open drain carrying the wastewater, and this is the pipeline. And this pipeline is the municipal water supply line that is crossing the drain. And the key feature here is they have got a joint at this location. The pipe is joined at this location and the waste stream is like this. And most of the times this is in a submerged condition. See, jointing, wastewater flowing, submerged condition. That's a typical case of a cross connection. And even you must have seen such a situation at many places. Like that, cross connection can be a contributor to the contamination in the water distribution system. So this is actually a summary of what is going in and what is coming out. So treated water, good quality water enters. You have got inline reservoirs. Reservoirs can also impact the water quality because I give an example of my 1000 liter overhead tank. I have seen a settled solids there. Imagine a reservoir, municipal reservoir having lakhs of water storage. What must be the condition there? So if it is not regularly cleaned, that reservoir itself can act as a source of contamination. So all this will go into the distribution pipeline. Treated water, cross-connected water, soluble particulate matters, and they will be subjected to these kinds of transformations, and you are going to get the output. And let us see in detail what these transformations are and how these transformations are going to occur in a distribution pipeline. And these are typical things that normally occur. So you have got a metallic pipe subjected to corrosion, loss of material that goes as a corrosion byproduct. Then these corrosion byproducts will get deposited, or if the water itself is hard, it may also form a scale. So corrosion end products with a scale that can form a deposit on the pipe surface, and these are the loose deposits. Depending on the velocity of water, they get scoured off, so they will enter into the system, and this is where the microbes grow. You have got organic compounds in the water, dissolved organic matter. If bacteria escaping from the treatment plant are present, so they will form a layer that is a biofilm, and this biofilm thickness increases. It will not sustain it too thick. It gets detached, and that covering will bring those microbial products into the water. If the waters were suspended solids, it gets deposited. And if the material of the pipe is not of that good quality, the pipe material itself will leach. For example, the plastic pipes can leach the lead. That can be a good example of leaching. So all these outputs ultimately enter into drinking water, and they will be part of your supplied water. So you may get suspended solids, you may get red water because of corrosion, you may get the bacteria contaminated water in your drinking water supply. This is a summary of the mechanisms that occur in any distribution pipe. Now let us come to what is there. So these are not the photographs accessed from any internet source. These are actually the pipelines that are taken out from a water distribution system as a part of rehabilitation from one of the cities that is going for a smart city in Maharashtra. These are the pipelines which are taken out of water distribution system from one of the cities in Maharashtra, and that is being implemented with a smart city program. So you can see the condition of the pipeline. So this is a cast iron pipe. That is what I was referring to. In the earlier, the people used a cast iron pipe. You can see the deposit. Earlier, the diameter of the pipeline was this. The time of taking out, it was the diameter. Nearly 50% of the diameter is reduced capacity is reduced. Look at the inner surface, it has become rough. Roughness coefficients are very high, head loss is very high. This is one photograph. So you can see this is what is expected. This is what is expected, but this is what we have. And you can see a lot of corrosion end products, bacterial growth, etc. So this is actually taken out, but I don't know how many of such pipes are still there, because they have got a fund for smart city. They have got the flexibility of taking out these pipes and rehabilitating it. But a municipal council or a corporation, shortage of funds, in spite of knowing that such pipes are there, age-old pipes are there in the distribution system, still they are unable to replace that. So you can predict, or you can visualize, or you can imagine what kind of water quality must be available in such localities. So this is the actual condition in most of the cases. And this is another photograph that is actually collected from the city that I was referring to. So actually we got a assignment for assessing the water quality, and when the water supply started, there were some reported contamination from some zones. We actually collected the water, and the water supply started in the initial half an hour. This was the water that was received or that was collected from the municipal taps, and over the period of the time that got into this quality, still not potable. Initially it started with this quality and this, and then we did some experiment with such pipe pieces. We collected such pipe pieces, and we wanted to know if we simply keep the water in such pipe sections, how much leaching is going to occur, or how much of the contaminants they get they enter into the water. So for that we took some pipe sections, we conducted some experiments, and we conducted the experiments for about 1.5 hour batches, and you can see we put a clear less than 1 NT water, and these are the different qualities that we got from different pipe sections. So every time we put a new batch, we could get such a quality. So it shows that whenever the water is supplied through such a pipe sections, the material which is attached over here, it is bound to enter into the water being supplied, and that is why you can see such a water coming from the different distribution pipelines. These are some of the real life examples where the people have experienced such a water in their taps. Now this is about how the water gets affected for its quality, right from the treatment plant to the customer end. Now let's look at some of the quantification. So if you want to quantify the water quality arriving at your customer tap, how to quantify it? Actually, there are 3 parameters. One parameter that can be actually measured. The other 2 parameters can be simply computed, or that can be simulated, or you can use it as an imaginary parameter or a virtual parameter that will tell something about its quality. So the first parameter is the constituent concentration. So you can assess the water quality actual by measurement. So I can measure the turbidity, I can measure the hardness, I can measure TDS, so I can measure any other water quality parameter, so that I can call as a constituent concentration. And when I talk of most of the municipal water authorities, and I interacted with so many people in and around Sangli, they tell one simple logic. Whenever a person who is monitoring the water quality in the distribution system, he will go with a orthotoluidine indicator, that's called OT indicator, and he will collect a sample and put 1 or 2 drops of OT indicator. When that water gets developed to the yellow color, so that person is also happy, and when it is reported to officer is also very happy, because they can foresee chlorine in that. But that is not the only case. So chlorine is not the only parameter that will tell about the quality of the distributed water. But unfortunately, we don't monitor for other parameters. We monitor only for the chlorine. But it is possible that any constituent can be taken, and you can monitor the quality at different places in a water distribution networks. And you can think of multiple constituents, especially if you are supplying the water from a river, hardness and TDS, they are not a problematic parameters. But what I suggest is when a water network is to be monitored, we need to monitor three parameters. One is the bacteria, that's the pathogens, through most probable number, MPN. We can find out the BOD, that is the dissolved organic matter, maybe in the form of BOD, and a chlorine. So if these three can be monitored properly, then I can get a fair idea of the distributed water quality. Normally, we have monitored a part of Miraj water supply, part of Sangli distribution system. We don't find much of variation in TDS, hardness, etc. But you can find a variation in turbidity, chlorine, and the pathogens. So in that sense, identifying a water quality in terms of multiple constants is going to be a significant effort. And the other two parameters are water age. As we know that if you store the water for a longer time, you may have a more chances of contamination. That is why normally we prefer fresh waters. But because of the concept of rainwater harvesting, etc., people have stored the water for a longer period, and they are being used without much of a problem. But especially when the water spends more time in a distribution network, then it is likely to be contaminated more, provided you have the sources of contamination in the distribution system. That is why age of water in a water network is a parameter that I cannot measure. So I cannot go to a customer tap and I cannot measure a water age, but I can calculate, I can simulate it, or I can use a model by which I can find out the water age. So in that sense, it is a non-specific parameter. It will tell something about the overall quality, but it may not be as effective quality as that of assessing a particular constituent. And we'll see how to find out water age little later. The third is source stress. Actually, if you are supplied with the multiple sources, then this parameter comes into picture. Otherwise, there is no use of this parameter. The meaning of source stress is, if I am supplied with only river water, one source, then the source stress is 1. All the nodes, all the customers are getting 100% of water from the river itself. But when you are supplied with 2 or 3 sources, and if the water reaching at my house, 30% from a source, 60% from another source, and remaining 10% from another source, in that case, your source stress can be 0.3, 0.6, and 0.1. So that is how the blending of the different sources at a particular node can be assessed by using this particular parameter. That's why I told you constant constant is more physically measurable. The rest of the two, you can simply calculate and you can compute using some model. As far as the constant concentrations are concerned, so as I told you that we monitored some part of Miraj water supply network. Actually, this is a Google map superimposed with different zones of water network. As you know that water distribution system is normally a zone type of a system. We don't supply the water to the entire city from one reservoir. Normally, one reservoir, one zone. Using that concept, the people serve the water. This is a water treatment plant, and there are about 5 zones, and each zone or one zone, 2 zones supplied with 1 ESR. So there are 3 ESRs. 3 ESRs together serve a total of 5 zones. We try to monitor the water quality for different parameters, including TDS, turbidity, etc. And we took one zone near the treatment plant and another zone. Actually, we monitored all the 5 zones. So I'll be showing the results of only 2 zones, one near it and one away from the treatment plant. And there are some remotest locations we identified for monitoring the water quality. And this monitoring was done for a whole year. Our objective was to assess the seasonal quality throughout the year. So I'm just giving a results of a zone 1, that is near to the water treatment plant, turbidity, chlorine, and MPN. So MPN is actually the most probable number that is going to give the bacteriological quality. So if you can see this, you don't find the same turbidity. So actually 1 NTU is the standard as per the IS 10500. So you can see turbidity present in the water. So you can see the chlorine. As per the standards, the chlorine should be at least 0.2 milligram per liter. You can see the chlorine level. Somewhere it is very low, somewhere it is 0.2, etc. So that too, it is near to the treatment plant, just chlorinated. You can find some high bars over here. And you can see still presence of some MPN values. Wherever you have got high chlorine, MPN is not there. Wherever low chlorine, you have got MPN present. So like that, if you monitor the constituent concentration, not only depending on the chlorine, the other parameters, so that will give a fair idea of the quality of distributed water. So if you look at the other zone, it is slightly away. You can see the turbidity. You can see more turbidity. Then you can see still less chlorine level, and you can see still presence of the bacteriological bad bacteriological quality available. So the general conclusion that one can see over here is the treatment plant, a zone clear near to the treatment plant, away from the treatment plant, that matters. Even within zone itself, there are different samples which are taken near that elevated reservoir, somewhere in between the zone and end of the zone. So there also the water quality is changing, and you don't find a similar pattern. It is not decreasing. It is not that. Even you cannot apply any model for such a case. When you are getting such a random results, you cannot apply any model to predict it. That is the best way of assessing the water quality in any water distribution system is to go to the field, select as many as sampling locations, and get the sampling done and analyze it for these three parameters. I have not included the other one, the dissolved organic matter. That can be another parameter. So the objective of presenting these results is you can find such a variability in quality in terms of clarity of water, chlorine levels, bacteriological impurity, etc. Now let us focus more on the chlorine. So in the morning, Professor Mohan Kumar was referring to this term, chlorine attenuation, because most of the water supply systems in India, they depend on chlorination as one of the major disinfection strategy. So I'll just focus a little bit more on chlorine, then we shall go to the modeling concept. So this is actually a distribution pipe, and the chlorinated water enters in the distribution pipe. So if you are having a chlorine of say 1 ppm over here, you may get less than 1 ppm over here. So it means that the chlorine is going to attenuate, or the chlorine is going to decay, or the chlorine levels are going to reduce. So this is because of two reasons. One is the chlorine gets reacted with the bulk constituents. Bulk constituent in the sense it will react with the constituents which are present in the water. And what are those constituents? One constituent is dissolved organic matter, other constituent is a bacteria, and then about iron and manganese, inorganic components. See if they are present, so it is likely to react with that, and the chlorine level will get reduced. And this kind of a deterioration we normally call it as a bulk chlorine decay. That is one part. And the other part is the chlorine which is near to the pipe wall. Near to the pipe wall, it reacts with the pipe material, or it reacts with the deposits on the inner surface of the pipeline. So the pipe is metallic, the wall reaction is dominant. If the pipe is plastic, the reaction rates are lesser. So in that sense, if this pipe would have been a metallic pipe, if I am having 1 ppm here, I may expect 0.5 for an example. If it would have been a PVC plastic pipe, it would have been 0.7 or 0.8. Whatever is contributed by the bulk decay, less is contributed by the wall decay. So that is, whenever a chlorine flows through a pipe, it gets affected by two reactions. One is a bulk reaction, other is a wall reaction. And the combined result of this is normally called as a total chlorine decay or overall chlorine decay. And if you want to measure the chlorine decay because of the bulk decay in the sense with the constituent in the water, that one can do by simple laboratory experiment. And that experiment is normally done by using a bottle test. In this, we take a bottle that is normally a brown colored glass bottle. In that, we put a chlorinated water. Actually, the water in which we want to assess the bulk decay, in that we chlorinate it, first time chlorination, then we measure the chlorine concentration with respect to time. So I got the data time versus concentration. Using that laboratory data of time versus concentration from a brown colored glass bottle, so I can find out what kind of reaction is involved with, and what kind of what is the quantum of the reaction rate constant. So this you can do it for different waters. You can do it for raw water, filtered water, and distributed water. Raw water and sand filtered water, they are not chlorinated, but the distributed water is already once chlorinated, and you are doing the chlorine decay test on the rechlorinated water. So depending on what water it is, your decay rate will be different. So if you have got a raw water, decay rate is more. Sand filtered water, decay rate is less. Distributed water, decay rate is going to be still lesser. So if you can look at this, you are going to get a data like this: time and chlorine levels. So with respect to time, the chlorine level is going to drop in that brown colored glass bottle, and using that data and using the different models like zero order, first order, second order, etc. These are the applicable models. You can apply first order, second order, parallel first order. There are so many models, but in most of the cases, the first order kinetic is more applicable, and you can get the data like this. The laboratory data put in a particular kinetic model, you can see. So this is the blue curve indicating the chlorine attenuation, bulk chlorine decay for a raw water, bulk chlorine decay in a filtered water, not chlorinated, distributed water. So you can see a sharp drop. Its bulk decay parameter is 0.29 per day. Still lesser. So it is site specific or a water specific. Even if you collect a Krishna river water or some other river water, you may get different coefficient altogether. But the overall objective is the bulk decay parameter can be found out by using a laboratory experiment, and that will give a proper quantitative analysis. But when you want to find out the combined effect, or when you want to find out the wall effect, how much of wall reaction is going to contribute to the chlorine decay, then we don't have a direct measure of measuring the wall reactions. So for that, a via media approach can be, what you can do is you take a pipe piece similar to the one that is there in the water distribution system. For example, suppose I want to find out the chlorine decay in a cast iron pipe. You take a piece of a cast iron pipe about 1 meter length, close the bottom end, and then you put the clear water in that, chlorinate it, and do the experiment similar to the one that we have done in the glass bottle. Here the glass is replaced by the pipe section of that particular material, and do the similar kind of a experiment, time versus concentration, and whatever decay that you are going to get, so that decay is a sum of bulk as well as wall components. So that is, find out the overall decay. Already I know the bulk decay for that. Deduct one from each other. You are going to get the wall contribution from that. So like that you can do it for different pipes. I'll show some of the results for an example. So these were the actual studies conducted in a cast iron pipe sections for different chlorine levels, and bulk decay test was also conducted in a glass bottle, and for different diameter pipelines the overall decay test was also conducted. So this gives an idea of overall consumption, this gives an idea of bulk consumption. When you deduct the two parameters from each other, you are going to get a contribution from the wall parameter. So like that, diameter matters, material matters, and the quality of the water, that also matters. And like that, this was done for a PVC pipe. And as a part of the consulting assignment from some city, this was the, you can just see here the photograph that I have shown earlier, highly corrugated pipes. See the wall decay. Wall decay is contributing to this, and bulk decay is very less. So the pipe itself was a dominating contributor for this thing. Now this is how we normally quantify the chlorine attenuation, either in the form of a bulk decay or in the form of a wall decay. Because when you want to do the modeling or a simulation, you require the knowledge of the bulk decay coefficient and the wall decay coefficient, because these are input parameters for the simulation studies. Now, at this particular point of time, I have just covered the most of the things which are descriptive of the water network, quality aspects, and how bad is the quality from the water networks, and also a little bit touched upon the hydraulic part of it. In general, if you want to do any modeling studies in water distribution system, the modeling studies can be done under three parts. One is the hydraulic analysis. The second is you can do the water quality simulation, especially for age, trace, and constituent variability. And the third is you can do the calibration studies. Actually, calibration is the part and parcel of analyzing any existing water distribution system. Because when we design a system as a new network, I don't require any calibration because everything is known to me. I know the roughness parameters, I have assumed the nodal demands, etc. But when you look at a water distribution system that is actually in place, it is working. And when you want to apply, when you want to do the modeling studies in that, we need to assume some of the parameters. For example, just now I referred to age of water network, and I told that the roughness parameter is a function of age. If you take the case of a ductile iron pipe, when it is new, we assume that the Hazen-Williams coefficient as 120 to 140, more appropriately 130. But a DI pipe present in a network for 10 or 15 years, you may not expect 130 out of it because the deposits inside. It may be 100, 110, 90, I don't know. Whether it is 100, 110, 120, how do you know? You have to do some kind of a calibration studies. So you need to set the roughness, then you should compare what is actually present in the system, what this model is going to give. So to apply a model, the calibrations are very important. We'll discuss that later. As a hydraulic part, actually my objective in this presentation is to focus on the water quality, but I cannot move ahead with water quality simulation unless and until I know some background of a hydraulic analysis of the water network. The basic meaning of hydraulic analysis in a water network is, you know something like you know the reservoir water levels, you know the nodal demands, and you know the infrastructure details, length of the pipe, diameter of the pipe, etc. Then I want to find out what is the flow and velocity in different pipelines, what is the nodal pressure available, etc. That is the part that I want to get it from the hydraulic analysis. So this you can do either in a steady state picture, single period simulation, in which you don't have the time varying factors like demands will not vary, water levels will not vary, everything is constant. It is something like a photograph taken of a particular system. The second is a dynamic condition, wherein the reservoir water levels will vary, the demands will vary, every time the flow in the pipeline will change. Like that, we'll have a dynamic analysis. That we normally do it by a process called as extended period simulation. And again, in these two, there are two. One is demand-driven approach. The second is pressure-driven approach. So we'll just try to understand this step by step. In the demand-driven approach, the logic is, I expect some water from a particular node. For example, if I am expecting about 90 liters per second of water from this node, irrespective of whether the pressure available is adequate or not, I expect 900 liters per second. It is demand driven. I don't worry about the pressure deficient conditions. Even if the pressures are low, I draw this much of water from the network. And such kind of approach is normally called as a demand driven approach. But when you think logically, in the actual water distribution systems, at some areas the pressures are very low, and at such low pressure areas, if you are expecting a expected demand, then that may not be appropriate case. In that case, the people thought of this approach, pressure driven analysis. In the pressure driven analysis, the demand will vary. Demand will vary depending on the available pressure. Normally, they define the pressure requirements. If the pressure is above a certain value, then I can get the required desired flow. And if the pressure is below some minimum value, I don't get any demand, it's zero. But between this minimum pressure and the required set pressure, if it is going to vary, it's going to vary proportionately by using such a kind of a expression. So the pressure driven approach, as the pressure changes, the demand changes. And you are able to get a required value when the pressure is more than a certain value. Like that, there are two approaches that are followed in the hydraulic analysis of network: demand driven approach and pressure driven approach. And to whether it is a pressure driven approach or a demand driven approach, we need to follow some of the basics of hydraulics. We need to formulate flow equations, head equations, node equations. Then we should set up with some computational methods like Newton-Raphson and linear theory. And most of the computer models, they use these methods as a base, and they use different effective and efficient algorithms to solve these equations. And without computer modeling, you cannot think of hydraulic analysis. And when you come to the water quality simulation, the simple meaning of water quality simulation is I know the water quality at the source, and I want to find out the constituent concentration, waterage or source stress at the customer end. So this is what we need to simulate or model in the water distribution system. But to go for this, you require the hydraulically analyzed network, because you should know the flow, velocity, picture clear. After that, I can analyze the network for water quality analysis. And in the water quality simulation, typically there are two situations. One is a steady state, other is a dynamic. So steady state is a little bit simple to analyze, and dynamic is a little bit complicated. For steady state, you can make use of simple dilution equation. So at any node, you can work out the mass balance, the total mass entering into a node and the total mass leaving the node. If you equate the two, and you can find out the quality that is associated with that particular node. So steady state model, you can work it out in that particular way. But for working out the dynamic model, the people have developed different techniques. There are two broad techniques that are adopted. One is called a time-driven method, and other is the event-driven method. And the softwares which are in use, they normally adopt either one of these methods. Ultimately, using this mathematical logic and applying the different kinetic expression. This is a first order kinetic expression. Even you can go with the zero order kinetic expression. Reaction rate you can define. You can define the transport by using a advection reaction equation for a dynamic water quality model. Then you could be able to find out the concentration entering a node and the concentration leaving the other node. Because when you represent a pipeline, there is an upstream node, a downstream node. The quality at the upstream node and the quality at the downstream node. So you can relate by using this advection reaction equation, and you can do the calculation. And similar mathematical formulations one can do for reactive or non-reactive. So if you are non-reactive, then there is no question of any reaction. Only the concentration will decrease by the dilution. But if it is a reactive constituent, then you need to supply the wall decay coefficient, bulk decay coefficient, etc. These are the mathematical formulations that are required. And so if you want to, these were for a single constituent like a chlorine. But when you have got a multiple constituent like you have got a bacteria, you have got a dissolved organic matter, then you have got a chlorine, all the three together. So in that sense, you require a slight change in your modeling concept, because there are three components involved: organic carbon, then this will actually the source for the bacterial growth, that is the food for the bacteria, then the biofilm will grow, and these are the factors that affect organic carbon, disinfectant level. All these are the factors which govern the bacterial growth. And ultimately, whenever you want to control the growth of bacteria in the water distribution systems, we should have a different strategies. One is either you can have a adequate disinfectant, see that the bacteria will not enter into the distribution system, or you reduce the organic matter. you make the bacteria shortage of food, so they will not grow. And in Indian context, disinfection strategy is adopted, so to control the biofilm growth. In that context, the development of this model having a carbon, organic carbon, bacteria, and chlorine is going to be a model that one can develop. So in that sense, a model was developed. Actually, it is a part of my PhD work. So this kind of a model was developed, and this model is applicable for the multi-components, 3 components: dissolved organic matter, bacteria, and the chlorine. And again, the advection reaction equations were used based on the molar kinetics. So I'll not go into the details of these equations. So ultimately, when you want to analyze a network hydraulically or for water quality simulation, especially when you want to work with a network model or a computer-based model, this is what you require, because I cannot think of doing it manually. For a large network having thousands of pipelines, we need to depend on the model. But any automation model works in these steps. You require a data. You require a data for the network. You require a data for a pipeline, diameter, length, roughness. You require the node data like elevation and base demand. Then you require the reservoir details. Then you need to specify the conditions, demand pattern, it is variable, steady, dynamic, etc. Then the hydraulic model will give you the flow velocity, head loss, and nodal pressures. And then the water quality model will come into the picture, and it will give you the constituent concentration, waterage, or a trace, the source trace. And these are the models that are available. So actually, in the earlier days, the people used a branch, loop, etc. So nowadays they are not used. Recently, the most popular model that is available in the free domain is EPANET. EPANET is one of the freewares that is very flexible. Even the Environmental Protection Agency, in their site, they have given the source code also. That is why in the morning I saw one EPANET and MATLAB combination study done by one of the students under Professor Mohan Kumar. Why these studies are possible? Because the source code is available. The source code of hydraulic analysis, the source code of water quality simulation is available in the EPA site. You can take those source codes, you can develop your own model, and you can carry out many studies in your water distribution system. And there is another popular software developed by the Bentley organization that was earlier known by the Hested methods, WaterGems. WaterGem is a commercial software you have to purchase, but EPANET is a free software one can use for the simulation or analysis. And there are other softwares, KY Pipe, CyberNet, and even some of the IITs have developed their own software. But EPANET is more flexible and easy to use. So typically, if you look at a simple network, and if you want to analyze it, so actually this is run in the EPANET platform. So I will not go into the EPANET. So it is very simple and easy to access. What you can do is you go to Google and simply type EPANET. You will be taken to a EPANET site, and hardly 3.5 MB software you can download within a fraction of a second. Immediately it will be installed, and you can draw such kind of networks with all loops, nodes, etc. And you can input the data of the required parameters for a pipe and node, and even the quality parameters you can input, and you can run the analysis. And within a fraction of a second, you are going to get the result. So this is how you typically get a result of a hydraulic analysis or a demand-driven approach from EPANET 2.2 version. This is the pipe parameters, the node parameters, and what conditions they are used over here. And the same network, if you run it for pressure-driven approach, you will get the result. So if you just notice the change over here, you can see that the demand, the flows in the pipeline, 475 and 425, total is about 900. It is not concerned with the pressure availability, but if you can see over here, it is 300 odd. it is less than 900. In the earlier case, it was 900 together. Irrespective of the pressure available, you are getting 900, but the pressure was deficient because the pressure criteria were mentioned over here between 0.5 to 7. The pressure deficient conditions were induced, and because of that, you will not be able to get the required nodal flow under such a condition. Same network, same thing, specifying the pressure, will be getting a pressure driven analysis. So like that, you can analyze the different scenarios in the EPANET and you can get the results. So this is actually one of the simple way of finding out the chlorine concentration in a steady network. So just now I told that mass balancing. For example, so if you look at this node number 2, this is a flow and this is the reaction rate in the pipeline and the node quality available over here. So if you simply write a mass balance, mass going in and mass going out. And whenever you find the mass going out, you should take the nodal flow also into account, nodal flow into the concentration associated with C2, write a mass balance, solve that equation, you will get the value. So like that, every node written with the mass balance from the initial reservoir level of 2 ppm, you can find the chlorine concentration at different levels. So for a steady state, in this way, you can simply calculate the value. And if you want to find out the water age, calculating water age in the steady state is again very simple. For water age, what we need to do is you need to understand the or get the travel time in the different pipelines. The water age is 0 at the reservoir, and when it comes to the node number 1, it will spend a time of the travel time. Suppose if it is spending a time of 5 minutes, the water age here is 5 minutes. So all the water leaving the node number 1 has got an age of 5 minutes. And when you come to the node number 2, node number 2 is connected to only by this particular pipeline. Age of here 5 plus this time 5 plus 10, 15 minutes is the water age at the node number 2. All the water leaving the node number 2 have a water age of 15 minutes. When you take this, it is 5 minutes, 5 plus 5, 10. This is 15 plus 5, 20. So 20 age water, then 10 age water with different flow rates arrive at node number 3. You write a mass balance here. Age into flow, you will get the age of water at the node number 3. Like that, a water with a 0 age will have 5 minutes of age here, 15 minutes of age here, and 14.5 minutes of age over here. Like that, using simple 0 order concept, one can calculate the water age. And similarly, one can do a simple calculation for a source stress for a steady state network. Two sources, how much of water is contributed from A to this, how much of water contributed to 3 from B. The sum of this contribution should be equal to 1. So like that, one can do the simple calculation to do this. But the same thing in the dynamic case is not that simple. You need to adopt a specialized systems of analysis. Now let us look at the applications of the steady state model. Actually, these are the results that are obtained from the model developed by myself under the guidance of Professor Mohan Kumar. But even if you put this network in a EPANET, you are going to get the same results as well. This is a typical steady state simulation analysis. So actually, it is not a detailed map of water network of mineral water supply system. It is a network of transmission mains. Transmission mains connecting the different reservoirs from the different source. There are actually 3 sources, source 1 and 2 and 3. Then for this, the bulk parameters, wall parameters were assigned, and from every source 0.75 megamolar of chlorine was induced. And then it was observed that at a node number 41, it is somewhere here, maybe a reservoir, one of the reservoir locations, you can find the concentration to be very less, minimum, and age is very high, about 10 hours. Minimum age, maximum age, minimum concentration, and that is how it is combined. When the water is going to spend more time in a network, it will have a lowest possible of chlorine concentration. And you can also find out the contribution from the different sources as well. So this shows that however the complicated network you have got, so if you have a model with you, you can get such a picture, and this will help you to do some strategy. And similarly, another network was taken. This is a little bit complicated network. Complicated in the sense it is served with a pump, and this pump will be on and off. It is serving for 6 hours. Next 6 hours it will not operate. Another 6 hours it will come back. So like that, 6 hours each it is operated, and that you have got a tank. Tank is being filled. The tank is being emptied with different water levels, and the water pipelines were associated with different wall reaction constants. And we analyze this network for a fluoride as a non-reactive contaminant and a chlorine as a reactive contaminant, and you could be able to get such a kind of a variation at different nodes. So I'm just showing these pictures because looking at the complexity of this network, the use of computer model will help you to give the time-wise variation in the conservative or non-conservative chemicals. And this is another complicated network in which you have got 2 sources, and this river source is controlled by the tank water level. So if the tank water levels are below and above a certain level, this will be off or on. And lake water is supplying the water for initially 15 hours. And there are 3 water tanks in this system. And under these constants, different controls, even if you want to predict the chlorine concentration, it is possible. Like that, the software can give or the computer model can give. So you can just see over here. You can see TDM, EDM net, EDM, etc. So actually, TDM and EDM are the method developed by some other people, and this EDM net is the one that is developed by us. So it is just a comparative study of how our model is performing at par with the other models. Actually, the TDM is a part of your EPANET software also. Even if you run the same network, actually these networks were taken from the EPANET itself. And even if you run this network, you are going to get the same water quality. Like that, you will get a water H simulation, source trace, etc. And more importantly, the model that was developed by us was applicable to the multi-component. When I worked on this problem, so that attachment was not there in the EPANET, but nowadays they have got an addition of this multi-component model in the EPANET model. So thereby you can use that multi-component model to predict the multi-components or the multi-constituents in the water supply system. So this particular network was taken, and this system was studied. If you have got the 3 components induced at the source, how they are going to spread, and if there is a contamination, if there is a leakage occurring at any point, and if you are going to induce the leaking water into the network, how it is going to spread. So with the use of that dynamic multi-component model, you can find out the chlorine levels at different levels. You can find out the substrate, there is a dissolved organic matter at different nodes. Even you can find out the biomass concentration for the contaminant intrusion. If the contaminant has entered, has spread, how you are going to get a spread of biomass and chlorine, etc. So like that, you can analyze the different pictures for this thing. Whether you apply a hydraulic model or a water quality model, so this calibration is very important. That sometimes it is called inverse modeling. The concept of inverse modeling is you know the end result, what is available, and you know what is being put in, and the model is giving something else. The model predicted and the actual, if they are same, then you don't require any calibration. But when your model predicted values and the end the observed values are different, then you need to adjust something in the network. So if you are doing a hydraulic calibration, you need to adjust the roughness parameters, or you need to adjust the nodal flows, so that the pressure monitored at any place is the pressure simulated or given by a computer model. Like that, you can do the hydraulic calibration. But when you come to the water quality calibration, as the sir was suggesting in the morning, you need to calibrate it for the wall reaction parameter. So that wall reaction parameter is very difficult to determine in the field. You can take it as an unknown, and you can measure the quality. For example, if I am doing the chlorine studies in the water network, you measure the chlorine concentrations through sensor or other methods at many places, apply the water quality simulation model, predict the chlorine concentration, and compare the observed chlorine concentration and the monitored chlorine and the model chlorine concentration and find the difference. And whichever KW gives you a closer relationship, that you can adopt it for further simulation. Like that, you can do the water quality calibration. And another part of the problem in most of the network is, especially it is true for chlorination, as it is said that you need to maintain 0.2 ppm of chlorine. If you want to maintain 0.2 ppm at this point, at a remote point, normally the municipal authorities will ask you, if I want to maintain 0.2 here, how much of ppm I should have at the water treatment plant? It is an inverse modeling case. To maintain a certain residual chlorine, what should be the injected chlorine? So if you are going to find out this value, that is called a source strength. Source strength indicates is the chlorine dose that need to be decided to have a chlorine of 0.2 ppm or a specified value available at the remotest point. So if you are able to maintain a minimum value here, I can maintain the value of more than 0.2 everywhere else. Like that, source strength and calibration, these are the inverse problems. They are addressed by using a different kind of a model. Actually, the IPANET model that is available, that you can use it as a trial and error for fixing the source strength. But if you want to get the actual source strength in one shot, you need to develop your own model. So in that sense, we too developed a model that was helped us to find out the chlorine concentration for required chlorine in the remote point in a distribution network. But the present version of IPANET, you can use it as a trial and error version, trial and error for fixing the source. And so I'll not go into these details. I'll just give the application. So again, I refer back to the Bangalore network that I described. And we simulated that the node 41 was the critical node where I was getting, or we were getting a 0.14 milligram per liter. But suppose if we want to get 0.2 ppm here, so that everywhere it is more than 0.2 ppm, what should be the chlorine injected at source 1, 2, 3? So that was assessed by the inverse modeling technique using a genetic algorithm. So these were the values. If you inject 0.7 ppm, 1 ppm and 0.65 ppm at 1, 2, 3 and sources, you could be able to get 0.2 over here. So like that, you can fix the source strength under the steady state condition. But if you want to perform the same exercise in dynamic state, again it is very difficult. So that was also done for such a complicated network with hydraulically dynamic and with different wall reaction parameters. The two sources, again the critical node was identified here. The critical node was a 269 node where it was tried to maintain 0.2 ppm, and under dynamic conditions we worked out how much of chlorine is to be injected here and how much is to be injected here. You can find this. So this 0.2 is kept constant everywhere. It is every time it is 0.2. If you maintain the chlorine level at river at about 0.3, in the lake at about 1.8 in this pattern, then you are able to get 0.2. This is for one case, and this is for the another case. Case 1, case 2. Case 1 is for one type of a chlorine injector. Case 2 is for another type of chlorine. It is a first order and it's a second order. Case 1 is a first order and case 2 is a zero order reaction. So like that, you can work out on the study of water quality either as a part of a simulation, or you can work as a part of an inverse modeling. And all these computer models, whether hydraulic model or a water quality model, so they will not only be useful for designing. They are not only useful for analysis, but they are also useful for many aspects. So you can have a use of them in the planning stage. You can have a use of them in the design stage. You can get the optimal design of the network using the software, especially the software like WaterGems. It has got a optimization module. So if you give a set of parameters, so that will give a set of diameters that are optimum in nature, that will minimize the cost with a hydraulically efficient network. Even for the system operations, you can use these models for water quality improvement, like constituent tracking, chlorine level monitoring. You can use this. Even for the real-time operations, for automation, sensors, etc., you can use these models. even for the leakage assessment, then for the intrusion of the contaminant, maintaining the distribution system. So many applications you can have for this. But in spite of these models, if you look at the kind of supply we have got, 1 hour supply with varying pressures, another 2 hour supply with high pressure, you cannot predict the water coming to your house. All these models will work perfectly, effectively, and the situation is under control. Situation in the sense, the conditions that you assume, they are prevailing in the system. For the sake of modeling, if you assume some conditions, if those conditions are not similar or near to the similarity, then whatever predictions that we get, that may not be appropriate. So in that sense, all these modeling studies should be correlated with the actual observations in the field. So actually we should try to do more studies on the collection of the data for a particular operating condition. For example, from an elevated service reservoir, if the water is supplied to a particular zone for only 1 hour, you try to get more and more data on the quality aspects, hydraulic aspect like a pressure in that 1 hour, and try to simulate only that 1 hour condition only for that zone from that particular reservoir. So then you try to simulate the conditions, whether the model has simulated the one that you actually collected, gathered, or the model has given adversely different picture altogether. So that is how, in some of the cases, whatever we look at the modeling with some beautiful projections, some mappings, etc. So they are very appealing in nature. But the actual success of all these kinds of pictures is achieved only when we put them into a real operation. Because everywhere we may not have automation systems, everywhere we may not have ideal conditions of supply. In that sense, the selective use, appropriate use of a model with due consideration to the real life situation is necessary for the Indian conditions. So I just end my interaction with you with this question. If we are not satisfied with the municipal water, we are not satisfied with the modeling studies, if we are not satisfied with the quality of water, quantity of water reaching my house, then we need to think of what? We need to think of our own sources. In that sense, this can help you. And actually, this is my own source. As I started my slide with the Krishna River, wastewater entering the Krishna River, treated water being supplied to my house, I decided that let us not use municipal water, at least for drinking and cooking. I will have my own source of water. What I have done, I have developed a micro level rainwater harvesting system. So what I have done, it is again something different in logic. Even some of you can try it out. So this is the terrace of my house. And on the terrace, I have put some roofing system. So it is a non-corrosive roofing system. And then I have put all the pipes which are required for collecting the rooftop rainwater. And then I have got a typical system of treatment. So this is nothing more than a settling. I don't have any filtration, anything, nothing is there. I got a combination of pipeline. So actually this particular pipe has got another pipe inside. You can see over here. Another pipe inside. The water collected from this gutter, rainwater gutter, it will enter, it will rise. So it is something like a clariflocculator. So those who know the meaning of clariflocculator, we have a flocculator inside, but it is not a flocculator here. The water is direct in downward direction. It will rise, and when it rises, it will provide a scope for settling. The particles will settle. Then it will go to the second settling compartment. It's upflow settling, downflow settling. Then I got a tube settler. So I got a bundle of tubes over here. Again, they will help me to settle out the suspended solids. So if I require, I may put some sandbags over here. They can arrest some fine particles. When the water passes through these series of settlers, I collect the water over here, and that is collected in 2000 liter tank, 1000 over here, another 1000 over here, and I got another 1000 here at the ground level. So you can just see the water, rooftop water harvested. Normally, I will not take the first flush. The first flush is taken out. So once the first flush is over, repeated rainy events will be collected, and it will be collected into this tank. And if you can see the quality of the water, so this is the water that has gone in, and this is the water that is stored here. So normal concept of rooftop harvested thing is they collect it from the terrace, they take it to the sump at the ground level, then they pump it. But here my approach is exactly opposite. I collect it from the top itself, I store it at the top itself, and then I will put it into the supply. And at the point of use, I got a simple cartridge filter. I got a simple cartridge filter. That is also not required. From the an extra precaution, I put a cartridge filter and I filter it out. So like that, one can generate his or her own source of water, especially for drinking and cooking. So this is how it is done. And the extra water that is overflowing, that is connected to a borewell recharge. So that also one can do. That is for potable water supply. But as at an institute level or at an office level or as a public building, even the people can think of generating their own source as a non-potable water. So Professor Mohan Kumar was referring to recycling of wastewater in the morning. So actually, this is a small treatment plant in our college campus, Walchand College of Engineering, Sangli. It is a DST funded project. We developed a integrated wastewater treatment system using a constructed wetland as a base of technology. We have got a baffled and biorack wetland followed by vertical flow wetland, and it is treated with it is used for treating a domestic wastewater. Using this, we are able to get a product water that can be recyclable. So it can be used for a flushing of a toilet, gardening, or even for the groundwater recharge. So like that, you can have your own source for developing. This is another recycling treatment plant installed at another nearby college. Actually, it is a project under my guidance of one of my PhD candidates. He also developed a system for grey water recycling. So in that sense, one can think of using a recycled water for non-potable usage, so that we can depend on our one. And I referred to these literatures. My work with Professor Mohan Kumar I covered, and my work with my two students, Kautekar and Pore, for MTech dissertation I referred to. So thank you for the patient hearing. If you want to interact, actually, I could not touch upon EPANET. EPANET is a self-explanatory software. Many of you may be using that, but it is a self-learning. You can use it at any point of time.
Yes. Any one or two questions, please?
There is one query in chat box. Could you see, sir? Could you just read it?
1 minute. I'll just see.
Pradeep Kumar Yagma Padluru. Pradeep, can you speak?
Yes, sir. Thank you, sir.
Yeah.
Good afternoon, sir. Sir, in Belgaum, we have many RO outlets, sir, to supply good potable water, sir. So if you put 2 rupees coin or 5 rupees coin, they will be getting 20 liters of water, sir. Now, in certain places, the courts, they have banned it, sir. I just wanted to ask whether they are safe. This is one question, sir. And almost 50% of water is lost, sir, during that process. Can we use that the wastewater that is coming out of the system to recharge the groundwater, sir?
So actually, there are two parts in this RO plant. Actually, recently we conducted an audit at Ichalkaranji. Whatever you are telling for a Belgaum city, a similar kind of a concept is being implemented in Ichalkaranji. So there were multiple RO plants installed, and they use the borewell water as the source of supply. So I think those borewell waters are in the vicinity of that Ichalkaranji Municipal Council. I think they must have permitted that. So if it would have been a commercial, then the legal complication may start. That is one part. If it is allowed, that is the source of supply. Even most of the packaged drinking water plants, they also use the borewell water as a source of supply. So they are not allowed to use the municipal water. That is one part. The second part is when the water is treated with purely RO. Purely RO treated water is not that safe because we are going to lose the minerals. That is one thing. But what these people do in the RO manufacturing unit, they bypass some of the water which has got TDS in that, and they mix it. The TDS containing water and RO treated water, they are proportionately mixed, and that is supplied. So if that is done, then you don't have to worry about the safety of the water because it is a TDS added and adequate mineral content is maintained over there. Then we need not worry about the quality of that. That is other part. And coming to the reject, RO reject, it is a fact that 60 to 70% of the water we lose as a reject. And for the reject, again, you have to use it for a different stages in the RO. That is one way of treating it. But at this particular moment, I don't see any technology that can effectively treat the RO reject. That is why what these people do, they put it as a groundwater recharge. So actually, putting it back to groundwater recharge, and it percolates to the ground strata, the TDS content will not go down. It will not reduce. Again, it will go back into the groundwater as a TDS rich water. That is unavoidable. That is a fact.
Thank you, sir.
Okay.
Hello, sir. Hello, sir. Am I audible?
Hi,
Good
you are
afternoon.
audible.
Sir, I am Maya from BIT Sindri, Jharkhand. My question is, sir, like if we are reusing the water, recycling the water and reusing the water, then how many times we can use the recycled water? Like how many cycles we can go for, and which will like what quality like determines how many number of times we can recycle and reuse water?
Are you talking of recycling for flushing? So if you recycle it for gardening, it will not come back. So if you are recycling it for flushing and you are again getting the same in the wastewater, are you asking this kind of a question, or your concept
Yes,
is
sir.
something?
Like what, grey water from wash area and kitchen, if it is collected and then recycled and reused, then how many times we can do it?
So I think when you are recycling a water, as long as, for example, let us take the case of a grey water.
Yes,
And
sir.
I treat the grey water to a standard that can be used for flushing a toilet, because nowadays the water quality criteria has been defined for flushing the flushing water for the toilet as well.
Yes,
So
sir.
when you recycle it, you are treating it and you are recycling it. I think the number of recycles may not come into picture over here.
Okay.
If this would have been a case for a cooling tower and other thing that is being completely recycled for cooling water, so there the TDS content will keep on increasing, and there we need to think of. But for treating such a kind of recycling, we didn't have to worry about it unless and until the quality criteria are satisfied.
Okay, okay, fine. Thank you, sir.
Sir, you are muted.
Dr. Shatrugna Singh, please be brief. And last question, please. This is
Okay.
last question.
Thank you, sir.
Be brief.
Okay, thank you. It was a very good presentation. Quick question about the quality of organic matter that will also affect during the chlorination process. So, don't we need to have some kind of measurement issues before chlorination for the organic matter quality?
Yes, sir. You are 100% right. That is what lacks in our Indian water quality assessment. Especially, we need to monitor the total organic carbon, TOC. So, TOC is going to be a parameter that is going to tell a precise, it is a precise quantification of dissolved organic matter. And if we know that, then only based on that value, we need to decide the chlorine dosage. Otherwise, the kind of source we have got and the kind of chlorine we add without any measurement, that is very risky. That will lead to the formation of THM. So your point is very right, very correct. We need to relate the dissolved organic matter in terms of TOC before deciding the chlorination strategy for a system.
Thank you, sir. Sir, a quick question, very quick question on your setup which you did at your house.
Shatrugna Singh ji, you can just directly interact with him whenever you find time, please. Okay.
Yeah. It's a question about the setup he has, whether he still pays the water tax or not. Because if you're not taking water from municipal corporation, whether they are still asking for the taxes or not.
No, sir. It is based on the quantity that we use.
Okay.
It is a metered water supply. The more you use from them, accordingly the bill will be generated from municipal authorities.
Okay, thank you, sir.
Okay, thank you. Madam, your mic is muted.
Nice presentation and informative, and many researchers and faculty members, they have got knowledge from your presentation, and if they require any help, they may mail you in case if required. Thank you very much for giving the valuable time.
Thank you, Mr.
Namaskar, sir. Namaste.
Thank you, Professor, once again for joining this one. And all the participants, so morning 2 sessions have been completed, and evening session is not a technical one. It is because you are having a lot of stress, and some of them are having so many other works. Okay, so in view of that, there is a general session on mental health management, how to do that thing. That will be taught by a senior, she is a senior deputy general manager from Kudremu Karan and Door Company Limited. It's a government of Karnataka undertaking, and she has lost lot of experience. And it's a general session. It is not a technical session. You please see that, because one session has to be in general regarding this personal management or stress management, etc. Because we know a lot of stress will be there, that you need to release it, so that how to manage that stress, because she worked from the last more than 30 years or so in that KIO CL Limited. So that's why we are reached 116. So please be back exactly at 2:30 sharply, and before that also you can join it. Please join exactly at 2:30 for that session. And there is one more speaker is there, that I will announce it at that time. Please join exactly at that time at 2:25 or so. Thank you. Please, you just have a virtual lunch. Okay, there is a break is there, virtual lunch break is there. You have your lunch, and please come back by 2:30 p.m. please.